A chatbot cannot tell you when a glacier will fall into the ocean. Scientists with the best equipment in the world have been trying to figure that out for decades and still cannot give you a precise answer. Yet something is now watching this glacier that none of those scientists ever had before. It was built for a completely different purpose. And what it found has the people who know this ice best preparing an obituary. What is the Doomsday Glacier and why does it matter? If the Thwaites Glacier were to melt away completely, it could raise global sea levels by 65 centimeters. Because it acts as a keystone holding back other ice sheets from flowing into the ocean, its disappearance could eventually unlock more than 3 meters of total global sea level rise. That 3 meters is roughly 10 feet. Coastal cities from Miami to Mumbai to Shanghai to London would face flooding that no infrastructure currently built is designed to handle. Hundreds of millions of people live in areas that would be directly threatened. Thwaites is a particularly important part of the Antarctic ice sheet because it holds enough ice to raise global sea levels by around 60 centimeters on its own, and is considered by many scientists to be at risk of rapid retreat, threatening coastal communities around the world. The glacier sits in West Antarctica and drains a massive area of land ice toward the sea. The amount of ice flowing into the sea from Thwaites and its neighboring glaciers more than doubled from the 1990s to the 2010s, and the Amundsen Sea region now accounts for 8% of the current rate of global sea level rise of 4.5 millimeters per year. The nickname came from scientists, not tabloids. A landmark 2014 study published in Science by Ian Joffin and colleagues at the University of Washington concluded that the glacier had already entered the early stages of collapse, and that rapid and irreversible collapse was likely within the next 200 to 1,000 years. The range is enormous, and narrowing it down is exactly what scientists and AI tools have been racing to do ever since. To understand why even the word collapse means something different here than in everyday speech, and why the work to pin down a timeline matters so much, you first need to understand what AI is actually doing at this glacier, and what it genuinely can and cannot tell us. What I can and cannot actually do here. When a video circulates claiming AI has pinpointed the exact year the Doomsday Glacier will collapse, the first thing worth knowing is which kind of AI is being discussed. There are two very different things happening, and conflating them leads to badly wrong conclusions. A chatbot like ChatGPT, or any other large language model, works by predicting statistically likely text based on patterns in training data. If you type, "When will the Doomsday Glacier collapse?" it generates a plausible sounding answer. It is not running a simulation, it is not doing physics, it has no access to satellite data. It produces text that sounds informed, but it is pattern matching, not scientific computation. Researchers who study these systems have documented a well-known tendency for language models to produce confident-sounding answers even when they lack the information needed to support them. The AI being used by actual glaciologists is entirely different. Scientists at the University of Leeds and University of Bristol adapted an algorithm originally developed to identify cells in microscope images and trained it instead to spot crevasses forming in the ice from satellite radar images taken by the European Space Agency's Sentinel-1 satellites. Crevasses are fractures in the ice that indicate stress building up inside the glacier. Finding them through snow cover, which blocks ordinary cameras but not radar, requires exactly the kind of pattern recognition machine learning is built for. This is machine learning trained on physical data to identify physical patterns. It is fundamentally different from a chatbot generating text about the future. These tools are being trained on decades of satellite radar imagery to find cracks forming underneath snow cover that humans cannot see, to track how ice is speeding up and slowing down, and to forecast how ocean heat is reaching the base of the glacier. The difference matters because one is a scientific instrument and the other is an autocomplete system. What genuine scientific AI is producing about Thwaites is far more sobering than any chatbot's guess could be, and far more grounded in verifiable data. The cracks that are already there. The most direct AI work on Thwaites involves tracking fractures in the ice shelf. Using machine learning, researchers taught a computer to look at radar satellite images and identify changes over the last decade. The analysis revealed that over the last 6 years, the Thwaites Glacier ice tongue sped up and slowed down twice, by around 40% each time, going from 4 kilometers per year to 6 kilometers per year before slowing again. When the ice flow quickens or slows, more crevasses are likely to form. Glaciologist Anna Hogg at the University of Leeds noted that this speed behavior was genuinely surprising. Dynamic changes on ice shelves are traditionally thought to occur over decades to centuries. Seeing this enormous glacier speed up and slow down so quickly was not what anyone expected. A separate detailed satellite-based study from the University of Manitoba, published in the Journal of Geophysical Research Earth Surface in 2025, tracked the specific structure that had been breaking the Thwaites Eastern Ice Shelf for decades. The Thwaites Eastern Ice Shelf is a partially confined floating extension of the glacier, anchored by an offshore pinning point at its northern terminus. Over the past 2 decades, the shelf experienced progressive fracturing around a prominent shear zone upstream of that pinning point, gradually compromising its structural integrity. A pinning point is an underwater ridge that grips the bottom of the floating ice shelf like an anchor, slowing its movement toward the sea. Once that grip weakens enough, the shelf detaches. The sequence of events observed during the terminal phase of the ice shelf is consistent with the initiation phase of a self-reinforcing feedback mechanism. This mechanism involves damage accumulation within shear margins, localizing strain concentration and promoting upstream acceleration, which in turn exacerbates damage further. If this feedback is operating, it is likely to accelerate disintegration. The self-reinforcing part is the critical detail. Once the process reaches a certain point, it feeds itself. Damage causes acceleration, and acceleration causes more damage. By May 2026, what had been a concern tracked through data became something visible and visceral to every researcher watching the satellite feeds. The changes were described by those who know this shelf most intimately, in terms not usually found in scientific communication. The year the ice shelf began to go. In May 2026, Robert Larder, a marine geophysicist at the British Antarctic Survey, who coordinates the UK side of the international Thwaites Glacier collaboration, made a statement that ran in Live Science and was reported globally. "The last bit of ice shelf in front of the glacier is poised to disintegrate," he said. "We don't know quite how this ice shelf is going to break up, but it's definitely going to go." Larder added that the ice shelf is very likely to break up in 2026. Karen Alley at the University of Manitoba, who had physically visited the shelf in 2019 and 2020, described what she was now seeing in satellite images. "It's dramatic," she said. "I was there in 2019 and 2020, and when I look at the satellite images now, I don't recognize the shelf. There are huge gashes where there used to be none." She added that it had gone from a thick, strong ice shelf that was very well grounded on the pinning point to a thin, weak ice shelf that is now splitting apart around the point that used to stabilize it. Christian Wild at the University of Innsbruck tracked the flow rate of the ice shelf over time and found something that alarmed him. The shelf's flow rate tripled from January 2020 to January 2026, reaching just over 2,000 meters per year, which he described as nuts. In the 5 months leading up to May 2026, it had accelerated further. "It's essentially in free fall now," he said. Larder also told reporters that an obituary press release for the ice shelf had already been prepared by his team, ready to go the moment satellite images confirmed its final breakup. If this is the kind of story that makes you want to actually understand what is happening to the planet rather than just scroll past it, subscribing keeps more of it coming. Because none of this means the glacier itself is about to slide into the ocean in one event. The collapse of the ice shelf is a specific and imminent thing. The full collapse of the glacier behind it is measured in decades to centuries, and understanding the difference between those two things is where the real story gets complicated. What the ice shelf was doing, and what losing it means. The Thwaites Eastern Ice Shelf has been a floating extension attached to the front of the glacier, like a traffic jam of ice, slowing everything pushing from behind. Ice shelves normally slow the flow of land-based ice by resisting the push from the ice upstream. However, observations and models show that the Eastern Ice Shelf had already lost much of its capacity to resist flow, and therefore its final breakup is not expected to cause a sudden, large acceleration of ice loss. It will, though, change how the ocean interacts with the newly exposed ice front and may alter the retreat rate. That note of scientific caution is important and often gets lost in coverage. The shelf breaking off is not the moment coastal cities flood. What it does is remove a break and expose more ice directly to the ocean, changing the geometry of how warm water reaches the glacier's most vulnerable areas. The science of exactly how this warm water reaches the glacier base was dramatically advanced by a study published in the Proceedings of the National Academy of Sciences in May 2024 by a team led by Eric Rigneau at the University of California, Irvine. The researchers presented evidence for seawater intrusions occurring at tidal frequencies over many kilometers beneath the grounded ice of Thwaites. Every tide, twice a day, warm pressurized seawater is being pumped kilometers beneath the glacier, where it melts ice from below at rates that existing models had not captured. The new data showed the process was reaching further inland than assumed, which means models that did not include tidal pumping were underestimating the melt rate. Larder explained the mechanism driving all of it. "It's more about the circulation of the water than warming," he said, "but indications are that human-driven climate change is ultimately to blame." Changes to the southern hemisphere westerly winds are what is driving warm water onto the continent, and those wind changes are part of the wider pattern of climate change. That fact, that some of the most consequential melt was happening in ways previous models missed, is why what happened next in a 2026 modeling study matters so much. The 180 billion ton finding. In March 2026, a study published in Geophysical Research Letters by Daniel Goldberg and colleagues at the University of Edinburgh and Dartmouth College offered one of the most detailed computational forecasts of Thwaites' future ice loss ever produced. The study's central finding was alarming, but its deeper contribution was methodological. Using satellite-calibrated ice sheet models, the researchers found that the Thwaites Glacier could be shedding 180 to 200 gigatons of ice per year by 2067, a rate roughly comparable to the entire Antarctic ice sheet's current total mass loss. To put that in perspective, Thwaites is already losing ice more than 5 times faster than it was in the 1990s. The 2067 projection suggests that rate keeps going up steeply, rather than leveling off. 180 to 200 billion tons per year from a single glacier, matching the current total output of the entire Antarctic continent, within roughly 4 decades. That number requires some unpacking, because the study revealed something even more important than the number itself. As Goldberg explained it, the method of calibration is not a technical footnote. It changes the future you get. Projections of sea level rise depend as much on how models are trained as on the ice itself. What Goldberg found was that 2 different ice sheet models, when calibrated against satellite data tracking how the surface of the glacier had changed over time, rather than just its current speed, produced projections that agreed with each other and showed continued acceleration out to 2067. Models calibrated only on velocity data tended to show the glacier stabilizing. Models trained on surface elevation change, which reflects the combined effects of melting, flow, and thinning all at once, kept showing acceleration. This is where AI enters the methodology directly. Goldberg described the calibration process as similar to how neural networks are trained. The researchers adjust hundreds of thousands of parameters. Traditional estimation methods will not work at that scale. The closest popular analogy is neural networks. They also have huge numbers of parameters that are adjusted iteratively to reduce error. The technique, called automatic differentiation, allows the model to learn from the observed behavior of the glacier over time, rather than just matching a snapshot of its current state. The result is that models trained on the glacier's trajectory, rather than just its position, see a very different, and much more alarming, future. Goldberg was also careful to note that the agreement between 2 independent models using this approach was what gave him any confidence in the result at all. He described himself as a skeptic when it comes to model predictions. One model showing something alarming is easy to dismiss. 2 independent models converging on the same alarming result is considerably harder to ignore. What the drilling expedition found and lost. In January 2026, a team from the British Antarctic Survey and the Korea Polar Research Institute reached the most inaccessible part of Thwaites Glacier, aboard the Korean icebreaker RV Araon. The goal was to drill directly through the ice to the grounding zone, the point where the glacier lifts off the seabed and begins floating, and to place sensors that would for the first time provide continuous direct measurements of ocean temperature and current at the glacier's most critical location. The team would drill 1,000 meters through the ice, just downstream of the grounding line. This is Thwaites' most vulnerable point, where the warmest ocean water flows under the glacier and melts it from below. Once complete, they plan to lower instruments through the hole to collect those first-ever long-term direct measurements. More than 40 helicopter flights were required to carry roughly 25 tons of equipment to the drill site over heavily crevassed terrain. What happened next illustrated how difficult this work genuinely is. Partway through the instrument descent, the team faced a major setback as the instruments got lodged in the ice, ending the research project before it even began. Keith Makinson, an oceanographer and drilling engineer at the British Antarctic Survey, acknowledged it plainly. Fieldwork in Antarctica always comes with risk. You have a very small window in which everything has to come together. The instruments were lost. The data was never collected. Scientists who had traveled for 3 weeks through sea ice, transported 25 tons of equipment by helicopter, and drilled 1,000 meters of hole, came home without the measurements they went for. A March 2026 follow-up expedition by the same teams reached an area slightly further seaward of the grounding zone and was able to collect some data, but the core instrument deployment had failed. This is the reality of glaciology in 2026. The glacier is changing in ways that demand answers. The tools to get those answers exist. Getting them to where they need to go, in the most hostile environment on Earth, remains extraordinarily hard. And US federal funding for Antarctic research, according to MIT geophysicist Brent Minshew, had been declining for decades, even before recent budget pressures, leaving a field grappling with a trillion-dollar problem on a research budget that barely moved since the 1990s. The tipping point question. The most consequential scientific question about Thwaites is not when the eastern ice shelf will break up. That is happening now. The question is whether the glacier as a whole has already crossed a tipping point, beyond which its eventual full collapse into the sea is locked in, regardless of what humans do about emissions. In February 2026, the Potsdam Institute for Climate Impact Research and the Max Planck Institute of Geoanthropology published a study in Nature Climate Change that mapped the tipping thresholds of different Antarctic basins. The Amundsen Sea Basin, which contains Thwaites and Pine Island glaciers, has the lowest thresholds of any Antarctic region, and might already be past its tipping point at today's roughly 1.3 degrees of global warming. Crossing a tipping point doesn't mean immediate collapse, the researchers noted. Large-scale ice loss in these regions unfolds over centuries, but the process may already have been set in motion. The study found that if the Amundsen Sea Basin has crossed its tipping threshold, the eventual commitment is approximately 0.9 meters of long-term sea level rise from that basin alone, not this century, over centuries. And reversing that retreat would require cooling temperatures below pre-industrial levels, a condition no current climate pathway anticipates. A separate landmark study from 2023 in Nature Climate Change by Caitlin Naughton at the British Antarctic Survey had already reached a deeply sobering conclusion about the ocean temperatures driving all of this. Rapid ocean warming, at approximately triple the historical rate, is likely committed over the 21st century, with widespread increases in ice shelf melting, including in regions crucial for ice sheet stability. When internal climate variability is considered, there is no significant difference between mid-range emission scenarios and the most ambitious targets of the Paris Agreement. That finding deserves to sit for a moment. Even if the world met the most ambitious climate targets ever agreed upon, the ocean warming driving Thwaites' melt was already committed. The heat was already in the system. Naughton put it plainly. "It looks like we've lost control of melting of the West Antarctic ice sheet," she said. "If we wanted to preserve it in its historical state, we would have needed action on climate change decades ago." How AI is being used to detect tipping points themselves. One of the most original scientific developments in this space involves using deep learning not to model the ice directly, but to detect the mathematical signatures that a system produces when it is approaching a tipping point. In 2021, a team led by Thomas Berry at the University of Waterloo published a study in the Proceedings of the National Academy of Sciences showing that a deep learning algorithm could be trained to recognize warning signals in time series data that precede a critical transition. The principle is that as a system approaches a tipping point, it slows down in how quickly it returns to equilibrium after being disturbed, a phenomenon researchers call critical slowing down. Deep learning algorithms can detect these signatures in noisy real-world data far better than traditional statistical methods. Applied to time series of measurements from ice sheets, ocean temperatures, or satellite records, this approach offers the possibility of detecting when a glacier system is approaching a threshold before it crosses it. The algorithm was also able to not only predict tipping points more accurately than existing approaches, but also provide information about what type of state lies beyond the tipping point, whether the system would transition abruptly or gradually. For ice systems, the distinction between an abrupt collapse and a slow-motion one is the difference between decades of warning and none at all. Separately, the British Antarctic Survey and the Alan Turing Institute built IceNet, a deep learning system trained on climate simulations and decades of satellite observations to forecast Arctic sea ice conditions months into the future. Unlike conventional forecasting systems that attempt to model the laws of physics directly, IceNet learns how sea ice changes from thousands of years of climate simulation data, along with decades of observational data. The system outperforms state-of-the-art dynamical models, especially for extreme sea ice events, and the team has been working on extending it to daily resolution and to Antarctic regions, including the Amundsen Sea. Applied to Antarctic systems, including the ocean temperatures that drive Thwaites melt, this kind of tool represents a genuine new capability, not to predict a collapse date, but to detect change and communicate it far faster than traditional modeling allows. What the full collapse timeline actually looks like. When scientists talk about the collapse of Thwaites, they are talking about a multi-stage process unfolding over different timescales, and clarity about which stage is being discussed matters enormously. The eastern ice shelf breaking up is happening in 2026. That is the near-term event, happening now, that researchers are watching in real time. The grounding line of the main glacier has been retreating for over 80 years. A 2024 study in the Proceedings of the National Academy of Sciences by Rachel Clark and colleagues at the University of Houston, using sediment cores collected from the Amundsen Sea near Thwaites, established that the modern phase of retreat was kicked off by a strong El Niño event and its aftermath in the mid-20th century. Once an ice sheet retreat is set in motion, it can continue for decades even if what started it gets no worse. The study's co-author James Smith at the British Antarctic Survey noted, "It is possible that the changes seen today on Thwaites and Pine Island glaciers were essentially set in motion in the 1940s. The full drainage of Thwaites itself, producing roughly 65 centimeters of sea level rise, is measured in centuries. The 2014 Jochen study placed rapid collapse onset at somewhere between 200 and 900 years from now. What the most recent science is revising is not the endpoint, but the rate in between now and then. The latest computer models predict continuing ice loss that will accelerate through the 22nd century and could lead to a widespread collapse of the West Antarctic ice sheet in the 23rd century. There is a consensus that Thwaites Glacier retreat will accelerate sometime within the next century. However, there is also concern that additional processes revealed by recent studies, which are not yet well enough understood to be incorporated into large-scale models, could cause retreat to accelerate sooner. The 23rd century for general collapse of the West Antarctic ice sheet, accelerating loss through the 22nd, and the warning that unknown processes could compress that timeline. This is the honest scientific picture. The people racing to slow it down. Not every scientist studying Thwaites has accepted its loss as inevitable. MIT geophysicist Brent Minshew co-founded the Thwaites Glacier Initiative in early 2025, a nonprofit that raised $5 million to fund research into both better forecasting and potential direct interventions to slow the glacier's retreat. Marrying traditional physics methods with new machine learning models, what they learn will feed directly into the design of interventions intended to, for example, increase the drag to slow or even stop the ice flow. The ideas being discussed include thermosiphons, devices dropped through kilometers-deep drill holes that would draw heat away from the glacier's base and refreeze it to the bedrock, and artificial speed bumps built into the seafloor to slow the glacier's slide. It will take years of research and development to understand if and how it might be possible to stabilize ice sheets. Minshew and his co-founder Colin Meyer wrote in a January 2026 op-ed in The Guardian, stressing the need for scientific discipline and environmental responsibility alongside innovation and speed. These ideas face enormous practical obstacles. Working in Antarctica, at the scale required, would be a logistical undertaking without parallel. Critics of geoengineering approaches argue the schemes are unrealistic and risk distracting from emissions reductions. Thwaites' own founders have said they are not advocating for any specific solution yet, only that the research to understand feasibility needs to start now, because if intervention is ever going to be possible, the window to figure out how is limited. What machine learning is doing in this context is helping close the gap between what researchers know and what they need to know to make any decision about intervention meaningful. Models that disagree by 3 feet of sea level rise over the next century are not useful for designing coastal infrastructure. Models that agree within a range narrow enough to plan around are. Verdict E. The actual verifiable record on Thwaites in 2026 is built from peer-reviewed science, named scientists speaking on the record, and formal findings from a joint US-UK collaboration funded by the National Science Foundation and the UK Natural Environment Research Council. The eastern ice shelf is in freefall. The glacier's retreat has been underway since the 1940s. The most careful current science puts the tipping threshold at a warming level the planet may already have crossed, and the models that best match how the glacier has actually been changing project ice loss rates by 2067 that would rival the entire Antarctic continent's current output from a single glacier. No chatbot produced any of that. Real scientists using real AI tools to process satellite data, train ice sheet models, and detect warning signals in physical observations produced it, piece by piece, over years of difficult and underfunded work in one of the harshest environments on the planet. The actual record is more alarming than any generated prediction could be, and unlike a chatbot's answer, every piece of it is checkable. If you want more deep dives that separate what is actually real from what is just a good headline, subscribing costs nothing and keeps this channel chasing down stories exactly like it.